Hello everyone. Today I will start one of the modulo of third semester of engineering mathematics. Course name is Transform Calculus, Fourier Series and Numerical Techniques, and code is 18MAT31, and this is common to all branches. Second modulo we will discuss today, that is Fourier series. Here in this modulo we will discuss these topics. First is periodic functions, next trigonometric series and Euler's formulae, Dirichlet's condition and Fourier series of period 2 pi, then Fourier series of even and odd functions in the interval minus pi to pi, and even and odd nature of f of x in the interval 0, 2 pi and associated to Fourier series. Next is Fourier series of arbitrary period, half range for Fourier series. Then last one is practical harmonic analysis. These are the contents we have to discuss in this modulo. Let us go to one by one. Before that, introduction of this Fourier series is Fourier series is an infinite series representation of periodic function in terms of the trigonometric sine and cosine functions. Means trigonometric Fourier series is an infinite series, and this is the representation of the periodic function in terms of the trigonometric sine and cosine functions. Then the second point is most of the single valued functions which occur in applied mathematics can be expressed in the form of Fourier series, which is in terms of sine and cosine. Next, third term is Fourier series is to be expressed in terms of periodic functions, sines and cosines. Fourth one is Fourier series is a very powerful method. This is very powerful method to solve the ordinary and partial differential equations, particularly with the periodic functions appearing as a non-homogeneous terms. Means this Fourier series is a powerful method to solve the ordinary and partial differential equation, particularly which are in the periodic functions and as a non-homogeneous terms. Next point is we know that Taylor series expansion is valid only for function with are continuous and differentiable, but the Fourier series is possible not only for continuous functions but also for periodic function with which are discontinuous in their values and derivatives. Further, because of the periodic nature, Fourier series is constructed for the period valid for all the values. This is the some introduction of Fourier series. Next, go through the periodic functions. What is meant by periodic function is a real value function f of x is said to be periodic of a period t if this function f of x plus t is equal to f of x when t is greater than 0. See, for example, sin x, cos x and the constant k are periodic functions of period 2 pi, and we know from trigonometry that sin of x plus 2 pi is equal to sin x, cos of x plus 2 pi is cos x. Also, if f of x is equal to k, then f of x plus 2 pi is also equal to k. Means x plus t. If the period t is 2 pi, then sin of x plus 2 pi is sin x and cos of x plus 2 pi is cos x. This is function Here, small mistake happens here. This is Function. Next is trigonometric series. The function k cos nx, sin x or sin nx, where n running from 1, 2, 3 and so on, are all periodic function of a period 2 pi. Taking the constant k is equal to a naught by 2, the linear combination of all periodic function is of the form f of x is equal to a naught by 2 plus summation n running from 1 to infinity an cos nx plus summation n running from 1 to infinity bn sin nx. Means the combination of all the periodic functions with a constant is known as the trigonometric series. This is known as trigonometric series where a0, a1, b1, where n running from 1, 2, 3, so on are all constants is called a trigonometric series. Hence, any function f of x expressible as trigonometric series of the above form must also be period with period 2 pi. Next is Euler's formulae. If f of x is equal to a naught by 2 plus summation n running from 1 to infinity an cos nx plus summation n running from 1 to infinity bn sin nx, means this series is defined in an interval of length 2 pi. Means when we define this f of x in the interval 2 pi, say c comma c plus 2 pi, and be considered as the period with period 2 pi, then we have, when we define this f of x in this interval, we get the constant as a naught is equal to 1 by pi integration from c to c plus 2 pi f of x dx, and an is equal to 1 divided by pi integration from c to c plus 2 pi f of x cos nx, and bn is equal to 1 by pi integration from c to c plus 2 pi f of x sin nx. The expression for finding a naught, an, bn are called Euler's formulae. When we define this f of x in this term, then the constants are a naught, a, b, an, bn are expressible as expressed as a naught is equal to 1 by pi integration from c to c plus 2 pi f of x dx, and an as 1 by pi integration from c to c plus 2 pi f of x cos nx, and bn as bn is equal to 1 by pi integration from c to c plus 2 pi for f of x sin nx, and finding these constants are called Euler's formulae. These are called Euler's formulae. Next is Dirichlet's conditions and Fourier series of period 2 pi. Here we have some conditions for the series f of x. The Dirichlet conditions under which the expansion of f of x has a trigonometric series will converge, means this f of x trigonometric series will converge to f of x at every point of continuity is, the conditions are f of x is single valued and finite in the interval c comma c plus 2 pi. Next is f of x should be periodic with period 2 pi, and f of x has only a finite number of discontinuities in c comma c plus 2 pi. Fourth one is f of x has at most a finite number of maxima and minima in c comma c plus 2 pi. These are the some Dirichlet's condition for the trigonometric series f of x. Thus, we can say that if f of x is defined in c comma c plus 2 pi and satisfy all these conditions, means Dirichlet's condition, then the trigonometric series, that is f of x is equal to a naught by 2 plus summation n running from 1 to infinity an cos nx plus summation n running from 1 to infinity bn sin nx is called as Fourier series of f of x in the interval c comma c plus 2 pi, and the constants are called Fourier coefficients. Next, remember this one. If f of x is continuous at x, then the series f of x is equal to a naught by 2 plus summation n running from 1 to infinity an cos nx plus summation n running from 1 to infinity bn sin nx converges to half into f of x plus f of x minus, where f of x plus comma f of x minus are respectively right hand and left hand limits of f of x with which is given by f of x plus is equal to limit h tends to 0 f of x plus h, and f of x minus is equal to limit h tends to 0 f of x minus h. You already know what is left hand and right hand limit rules, where h is greater than 0 and the end point of f of x converges to f of 1 by 2 into f of c plus f of c plus 2 pi. Remember this condition, means this note. Next, while solving examples, we have to know the Bernoulli's generalized rule of integration. That is, integration of u into v into dx is equal to keep u as it is. Here, consider u as a differentiating part and v as an integrating part, then which is equal to keep differentiating part as it is and integrate this v into dx minus, then differentiate this u, you get u dash, again integrate this integration of v dx, therefore it is double integration of v into ds plus again differentiation u double dash, then again integration v dx into dx minus, and so on. Next is, here we have some important formula here. Cos n pi is equal to minus 1 raised to n, sin n pi is equal to 0 for all n belongs to z. And these are the some important example you have to remember while solving example. These are very helpful results. We must know this result. Next, going to examples. First one, obtain this Fourier series of f of x which is equal to pi minus x divided by 2 in the interval 0 is less than x is less than 2 pi. Hence, deduce that 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus and so on is equal to pi by 4. Solution. The Fourier series of f of x having a period 2 pi is given by, we know that the Fourier series f of x which is equal to a naught by 2 plus summation n running from 1 to infinity an cos nx plus summation n running from 1 to infinity bn sin nx, name as this is equation 1. Next, we know the constants, that is a naught a1, a naught is equal to what and b naught is equal to what, sorry, a naught is equal to what, an is equal to what, and bn is equal to what. Here limits from 0 to pi, instead of c to c plus 2 pi, take 0 to pi, 0 to pi, this is 0 to pi. These are the formulas of Euler's formulae. Then to find a naught, a naught is equal to 1 by pi integration from 0 to 2 pi minus x divided by 2 into dx is equal to 1 by pi. When we integrate this one, we get, here 2 is constant, take outside 1 by 2 pi, then it is integration of pi minus x is pi keep pi as it is, difference integration of x, this is pi into 1 is, this is x minus a different integration of x square is x square by 2, because pi is constant here, integration of 1 is x, therefore pi x minus x square by 2, limits from 0 to 2 pi. When we apply the limits here, we get 1 by 2 pi Here it is 2 pi square minus 2 pi square minus 0. It will be 0. Therefore, a naught value is 0. Next, for finding an is equal to 1 by pi, integration from 0 to 2 pi, pi minus x divided by 2 cos nx dx. Applying Bernoulli's rule here, we get an is equal to 1 by 2 pi. Integrate this one. Here 2 is constant, 1 by 2 is constant, take outside. Here pi minus x into cos nx. Keep pi minus x as it is and integrate this cos nx. We get sin nx divided by n minus, and differentiate this. This is differentiating part here. Pi minus x is differentiating part and this is integrating part. Then differentiate this one, you get minus 1, and again integrate this sin nx divided by nx. We will get minus cos nx divided by n into n is n square. Limits from 0 to 2 pi. After applying the limits, we get minus 1 divided by 2 pi n square cos 2n pi minus cos 0. We know that cos n pi is equal to 1 and cos 0 is also is equal to 1. 1 minus 1 is 0. 0 into something is also 0. Therefore, an is equal to 0. Next is bn is equal to 1 by pi, integration from 0 to pi, pi minus x divided by 2 sin nx dx. Again by Bernoulli's rule, here bn is equal to 1 by 2 pi. Keep this pi minus x as it is and integrate this one, minus cos nx divided by n minus, then differentiation of this is minus 1. Again integrate this one, we get minus sin nx divided by n square. Limits from 0 to 2 pi. After applying the limits, bn is equal to minus 1 divided by 2 pi n, pi minus x cos nx, limits from 0 to 2 pi, and the second term is 0. Then apply this limits, we get 1 minus 1 divided by 2n pi minus pi cos 2n pi minus pi cos 0. We know that cos 2n pi value is 0 and cos 2n pi value is 1 and cos 0 value is also 1. Therefore, it is minus pi. It will be minus 2 pi. Therefore, this minus get cancelled and 2 pi get cancelled. Remaining is 1 by n only. Therefore, bn value is 1 by n. Thus, to reduce that series, we have to put, thus by substituting the values of an, bn, a naught, bn in equation 1, the Fourier series is given by f of x is equal to pi minus x divided by 2 is equal to summation n running from 1 to infinity 1 by n sin nx. Because a naught value is 0, an value is 0, only we get the coefficients of third one sin nx only. Therefore, it is summation n running from 1 to infinity 1 by n sin nx. To reduce the required series, we put x is equal to pi by 2 in the Fourier series of f of x. Therefore, f of pi by 2, substitute x as a pi by 2, which is equal to summation n running from 1 to infinity 1 by n sin n pi divided by 2. Now, we know that sin n pi minus pi by 2 divided by 2 is equal to sin pi by 2 divided by 1, sin pi divided by 2 plus sin 3 pi divided by 2 plus sin 2 pi divided by 2 plus sin 5 pi divided by 2 whole divided by 2 plus and so on is pi by 4. This is, when we solve this one, we get pi by 4, which is equal to 1 minus sin pi by 2 is 1 minus this value is 0 and it will be 1 by 3 plus again this value is 0, this is 1 by 5. When we continue this one, we get 1 by 7 plus and so on. We have